Yeah, I mean, we're not, coffee again, or soup?
I don't know.
Okay. Yeah, so yeah, I don't want to do the group presentations unless everybody's here, everybody from your group, so I can choose randomly. Okay, so in that case, I was planning to have you all do some group work today anyway, so think about stuff together. Okay. So remember where we were in the middle of doing the proof of the completeness of R, right? So we had this theorem that said that suppose we're in R, then a sequence is Cauchy. It's Cauchy if and only if it's convergent. It is convergent. Okay. So right. Okay. So let's see. And we already showed that the reverse direction, right? That convergent implies Cauchy, and we are in the middle of doing the forwards direction, showing that Cauchiness implies convergence, right? I said, okay, suppose your set is Cauchy, and we consider the set S, which is just the set of values, right? The set of values taken by the sequence, right? So, right, if your sequence is, for example, -1 to the n, right, then S is just -1, +1, right? It's the set of values taken by your sequence, right? Okay. And we said, well, there's two possibilities, right? Two possibilities. Two possibilities, right? S is either finite or S is infinite. Right? Either S is finite or S is infinite. Right? And you, on your homework, already showed that, so with your homework, to show that if S is finite, then the sequence A sub n must eventually be constant. Right? The sequence must eventually be constant, and thus converges, right? And thus converges. Right? In other words, you found there was some value. There had to be some value that this thing, became constant to. Right? And you remember the idea? The idea was that, well, suppose you have a finite number of values, value 1 and value 2, same, right? Then you know that, past some point, since the sequence is Cauchy, right? Since the sequence is Cauchy, you know that, right? So take the minimum distance, right? Let epsilon be the minimum distance between any pairs of values. Right? The minimum distance between any pairs of values. Right? Since the sequence is Cauchy, right, you know that past some n, right, all an minus am are less than epsilon. All an minus m must be less than epsilon, right? But that means that they can only take on one value, right? Past that n, you must be all the guys must be one value, because if they took two values, well, you'd have a distance greater than epsilon. I mean, you have a distance, equaling epsilon, right? Which is a contradiction. Okay. So thus, all a sub n for n bigger than n must take the same value. Okay. Right? Because if they took different values, well then, if, say, a sub n equals vi and a sub m equals vj, then the distance is greater than or equal to epsilon. Contradiction. Right? Because epsilon was the minimum distance. Right? Okay. So part two. So that's part one of the proof. Right? Part two. Suppose that S is infinite. Suppose that S is infinite. Right? That is that there are an infinite number of values that are taken by the sequence. Okay. Well, we want to say that the sequence converges, right? We want to say that the sequence converges. So here we have some sequence. We have some Cauchy sequence, right? Cauchy sequence means that the things are getting closer and closer to each other, but there's an infinite number of values, not just a finite one. Okay? And we want to say that there's some value, right? There's some value L that actually is the limit of the sequence, right? There's got to be some value L. We want to show there exists some value L such that your sequence converges to L. Okay. So how do we find that value? How do you think we're going to find that value? Anybody have an idea? Like, something. There's some theorem that might give us a possible value.
Completeness axiom.
That's what we're trying to show, right? Do you mean like?
I'm just throwing one out there.
Well, I mean, actually, that's related. That's related.
Least upper bound.
So least upper bound.
Bolzano-Weierstrass theorem?
Yeah. Okay. So that's the thing. So you guys, completeness, least upper bound, Bolzano-Weierstrass theorem. You guys are sort of going farther back, and Bolzano-Weierstrass theorem is the thing that uses the least upper bound. Okay, so Bolzano-Weierstrass. How do you use Bolzano-Weierstrass? What does Bolzano-Weierstrass tell you? You knew the name, but you don't remember the result.
Accumulation points.
There's an accumulation point, right? If you have an infinite number of points in a bounded set, right? You have a bounded set, and there's an infinite number of points in that bounded set, then you're guaranteed an accumulation point. Right? So Bolzano-Weierstrass says that S has an accumulation point. call it L. Okay. Great. Right?
And we know that S is bounded by?
Because
Cauchy?
Because it's Cauchy, right? Remember, Cauchy sequences are bounded.
Cool.
Right. Very good. That was what I was just about to ask. So, okay. So I want you to actually work on this. Okay, take a couple minutes and see if you can figure it out. Why is that? I called it L because it's going to be the limit, right? Why is that L actually the limit? Okay, so see if you can come up with ideas and talk with each other the next couple minutes. Yeah. Aria, the group, people's groups are not whole, basically.
Okay.
So
Well, I have our paper. Do you want me to give that to you?
yeah, but
I don't think
I
that
don't.
we're gonna be whole.
They must be. Yeah, I mean, these are group presentations, right? You don't show up to the group presentation with only half of your group. I don't understand that, frankly. The group should be here.
Didn't mean to. It just kind of happened.
Yeah, I'm sure it just happened, but it should not, right?
Okay.
Like if if there were a grade involved, it would be docked at this point, right? Definitely docked. Okay. Now okay, so have the group here on Monday, please.
Yeah, well, our person's like gone. Like he couldn't come.
Oh, he's like somewhere else.
Yeah.
And I was taking an exam.
Yeah.
And I mean, Haley is.
Okay, don't worry about it. Don't worry about
MIA
it.
half the time.
Okay, don't worry about it. Yeah, I mean, Haley should be here. Anyway, don't worry about it, but please take it a little bit more seriously. This is a group presentation, right? It's not like, hey, this is a group presentation. Yeah, and I mean, the point of these group presentations is to prepare you for the final presentation, right? Well, you don't just skip it, right? It's like, no, I don't need to prepare for that. Okay, that's you can think that way, but final presentation, you're gonna regret it. So yeah. Okay, so okay, now cheer up a little bit. Cheer up a little bit. There's nothing has happened. Nothing has happened. I'm just saying, if I were grading this group presentation, yeah. Okay, but that's not happening, right? Not this time. Okay. I want you all to think about Bolzano-Weierstrass. Think about Cauchy sequences. You got a Cauchy sequence, right? So part of doing mathematics is developing an intuition for things that don't exist, right? Things that don't have a concrete form. You've got a Cauchy sequence, right? Your sequence, the distance between two things are getting closer and closer, right? The distance between any two pairs is getting closer and closer, right? You've got Bolzano-Weierstrass that says that, so if you just look at the values, like look from the side here, you see all these values, right? You see that there's an accumulation point, right? There's an accumulation point. In other words, every punctured neighborhood of that guy contains an element, it contains one of the values. Okay. Why does that force that accumulation point to be the limit of the Cauchy sequence? Okay. Okay. So I want everybody to think. We'll do this as a group, basically. Think for 3 minutes. Think of like. We kind of already have the tools, right? You've got Bolzano-Weierstrass, you've got Cauchiness, right? How do those things go together? Think about how those things. Try to make an intuitive argument about how you could show that L is the limit of the sequence. Okay, so like why this would make sense to you. So think. You want to think. Why is it obvious that L is the limit? Right? Why is it natural? Maybe obvious. There's too much judgment in it. Like if you don't get it, what's wrong with you, right? But that's not what I mean. I mean that whenever you approach any bit of knowledge, you want to think, why is this completely natural? Right? It shouldn't be a miracle. Right? It's not a miracle. It should be complete natural sense. Okay, so that's how you want to think about your mathematics, right? Everything should be, oh yeah, That actually makes sense. Why is it natural that this guy should be the limit? Mitchell, you're looking at me. Why are you looking at me?
I think I have an idea.
Okay, good. Okay, good. It's like, does it help to look at me to get the answer? Maybe. I don't know. It always helped me to work outside of my professor's office.
Directly outside?
Yeah.
Because I never wanted to talk to the professor, right? But if I had a question, I'd go and I'd sit outside the door and I'd work my ass off trying to figure out what was going on before talking to the professor. And then I'd figure it out and I'd go home. Okay, so I want you, so everybody maybe talk to each other. I mean, actually, as a group, actually. I'd like you guys to like say things. And turn around, Hobin, Mitchell, you guys turn around, say things to each other.
Are we like one big group right now?
Yeah, one big group, yeah. One big group. There's not enough to make two small groups.
So the idea is like using what we had where all of the points have to be within epsilon of L. If you have the Bolzano-Weierstrass, it's every time you cut it in half, it's going towards a near point. So there will be a certain point that every time you cut it in half, it has the same limit on one side, upper bound or lower bound. And it's like that is your limit that your epsilon is getting smaller and smaller towards.
Is that like a very non-mathematical idea? because we defined subsequences before we decided to prove this, I feel like we might need to use subsequences.
So that's like a gamesmanship idea. Like that thing showed up in the game. It must be part of the solution.
Yeah. Well, one thing you could do, if you could prove that every subsequence of the Cauchy sequence converges to L, then you could say that the Cauchy sequence converges to L. But I don't know if that would be easier or harder than just proving that the Cauchy sequence converges to L.
How do you connect that to accumulation point? 'Cause we're trying to say that they're the same thing. Yeah.
The limit of, and the accumulation point.
I mean, I guess the accumulation point says that, like, the intersection with the, like, within epsilon and L is never empty, right?
Yeah.
So then, there's always an element that's within epsilon and L. And that sounds a lot like when we say, like, for n bigger than big N, you know, it's within epsilon, but.
Yeah.
If you guys want to use the board, feel free to come up and use the board, if you want.
How would we use subsequences in this case?
Just like intuitively, I feel like.
Is it better if
Every time you cut it in
just one
half.
question, is it better if I step outside? Do you feel uncomfortable, like,
No.
if I'm here? Okay, great. And also, second thing, are you sort of watching me for my reactions if I'm around?
Yeah.
No.
Yes? And I'm going outside. I'll be back in like 3 minutes or so.
So if we say that this is L accumulation point, and then we have this is A1, and this A2, this A3, A4, and so on, then we can say, okay, if you take all the odd numbers, they're all converging to L. If you take all the even numbers, they're also all converging to L. If you take any kind of different sequence, they're all getting closer and closer to L. I don't know how to put that in like math terms.
I think
So Jackie, you were saying,
add to what Julia was saying and say that, like, every time you cut it in half, it.
So right,
It's
doesn't
a
matter if you cut
subset.
in half like span wise or if you cut it in half like value wise. So like if you're only taking every other term or every seventh term or like terms however far apart.
So like each time you cut it in half, that's a subsequence, and then they keep
Mhm.
staying closer with that idea.
so then you have to show that all the subsequences?
For any arbitrary subsequence, therefore all.
My brain is a little fried right now.
Yeah, the test was
We had a
terrible.
2-hour exam at 8 a.m.
I had enough. I could not finish the derivations. I'm just like, I'm out.
It was like all
Bye.
derivations.
It was all
It was so
derivations.
much.
Half the test is derivations.
I don't get why he's not doing the group presentation. And then yelling at us.
You did all this numbers.
I don't care if it's a professional event, like, you have to.
I mean, I
learn
guess the
to-
point is we should have voiced, oh, we're not gonna be here type of thing, I guess.
Well, that's on Nick.
But those two.
And
haven't
me,
either.
I was late.
Well, I told him when I came in, I was like, oh, sorry, you might be 5 or 10 minutes late. You had a
Thank
test.
you.
And like, we all knew anyways. So it wasn't like that big a deal. The other two aren't even here. Anyways, like.
I think Marco had a pretty good idea.
Yeah, let's hear it. I mean, so you have some idea of how to pull it off?
Mhm.
That's great. Okay. So all of you understand it?
Well, I'm not sure that we got all the way, so Marco's idea was you could look at the subsequences and any subsequence is gonna converge to L, and then we were kind of combining that, like Jackie and Julie were combining that with their ideas about, you can take every, second term or every seventh term, for example, and have that be your subsequence, cutting it down.
Let me think. So, okay. So see if you can take the next few minutes and see if you can actually write something down. Right. See if you can actually write down something. Put together an argument. So all of you have faith, the group consensus, this is it, this is the way to go. Okay, yeah, I mean, nobody, that is to say, I'm wondering if people have other ideas, or if that was the main one.
Please
That was the main
speak
one.
now.
Okay, so yeah,
Hold your peace.
what'd you say?
Please speak now or forever hold your peace.
No. This is not like a marriage or something. Yeah, so see if you can sketch it out more precisely. The more rigorously, the better. Right. Sketch out the idea and then fill in the gaps. Yeah, and if you guys can actually come up with it, I'd love to see what you do. I mean, maybe you should even do this together. It seems a little peculiar that you're all doing it individually. Right.
So we've been finding the A1 through AK or something as subsequences.
Yeah, so I think maybe the way to do it, sorry to butt in, but maybe the way to do it is have somebody sketching it out up here, and everybody is saying, "Uh-oh," or "Yeah, we need to say this," or something like that. So, does somebody want to? Looks like Jackie is being volunteered by Aria. So write up, and I want everybody should be telling her what to do. Including herself, right? She should be saying what she thinks. And pointing out if something is wrong or this is how people work together in mathematics, in my limited experience.
What if we started off by saying that since A7 converges, every subsequence converges?
We're trying to show ways that converges.
Right.
Oh, yeah.
So it's more like our series AK is bounded, we know that because it's Cauchy, and therefore because of that, any arbitrary subsequence we have is also going to be bounded. And so if it's bounded by Bolzano-Weierstrass, then it must have an accumulation point.
What did you say? Because.
So she said the sequence is Cauchy, so the sequence is bounded, so every subsequence is bounded. That makes sense, if you have a upper bound for the entire
Yeah.
sequence, that's gonna be the same for
Yeah, that
any
makes sense.
subsequence.
That makes sense, yeah.
Maybe
And then-
Jackie, I'll do it for you. If that- I'll write, and you guys tell me what to write. I'll be the secretary. So, yeah, tell me what to write. So, how do you starting off? So you say, okay, we want to show that if the sequence is Cauchy, then it must converges, right? And A sub n converges to L. No, that's already been said. We want to say, we want to show that A sub n converges to L. To L, which is that L from over there, right? The accumulation point from the Bolzano-Weierstrass theorem. Okay, so how do you start off?
So if the sequence is Cauchy, then we know that for any epsilon larger than 0, there exists an n such that n larger than n implies that the absolute value of a sub n minus a sub of n is smaller than epsilon. And then somehow we should denote a sub n and a sub m as individual infinite bounded and infinite sets or sequence sets.
But those are just
Those are just values.
Those are just values.
Yeah.
Yeah, these are just values. Okay, right, so this is the Cauchiness, right? And you also know that, right, L is the accumulation point of the set of values, right? Accumulation point of S. In other words, given any epsilon, there exists some there exists some A sub n k, right, in the punctured epsilon neighborhood of L. Right, so those are your two facts. Right. Remember what you want to show? You want to show that A sub n converges to L. In other words, for all epsilon, there exists an n such that if n exceeds n, then the distance of A sub n to L is smaller than epsilon. Right? So we want to make everybody within epsilon of L. So we can make ours close together. We can always ensure that there's somebody inside the epsilon neighborhood.
So can we use the notation that you used there to say, like, because that's the same notation we use for subsequences, that also any subsequence will be within the punctured neighborhood of L. Will have an element in.
Well, that requires proof, right? So, I mean, if you say maybe you have a claim, so you say a claim. What's your claim?
The every subsequence of a k also has an a and k in punctured neighborhood of L.
Every subsequence what?
Also
Also converges. Also.
has an accumulation point to L.
Also has L as an accumulation point. Okay, so that requires proof. Right? You need to prove that.
Yeah, we kind of have the same problem.
Yeah.
Like, if you're proving that the subsequence has L as an accumulation point is a pretty similar problem to proving that the whole sequence is an accumulation point.
No, but we also have the theorem that's, no, that's again because we're trying to prove with the, so we have the theorem that says any subsequence has the same limit.
Yeah.
If
Or
there's a limit.
if all the
Right.
subsequences have the limit, then L is the same.
Yeah, but you don't know that you have a convergent sequence, right? So it's true. If this converged, then all the subsequences would converge to that
Oh,
limit.
it doesn't go both ways.
But you don't know. You don't know that,
Mhm.
right? This is what we're trying to show, that a sub n converges to a limit. We don't know that all subsequence converges to a limit. And you can imagine that you could have some sequence that has multiple accumulation points, right? Although then, maybe it wouldn't be Cauchy.
Which is our contradiction.
Well,
Can you say that again, Professor?
no.
Can we have multiple accumulation points?
Points, because it's always supposed to be within epsilon is that.
So,
So suppose, like proof by contradiction,
Yep.
suppose that
A
there are
sub n.
multiple accumulation points.
or suppose a sub n doesn't converge to L.
Those are two different statements, two very different statements.
Yeah.
Well, if you suppose that it converges to something that's not L, then your epsilon is within that other value, which is like M or something. And if you choose that to be half the distance between L and M, then it can never be by L. So your function neighborhood would not have, function neighborhood of M wouldn't have all the points.
So that could not be a function. Like that could not be an accumulation point.
Yeah.
So you start off by saying, if you're doing the proof by contradiction, so let's say an doesn't converge to L, then there exists some epsilon for which there exists no n, such that n greater than n implies that you are within that epsilon, right? That
I
would be
see,
the
so
first
you
thing.
were actually saying like let it converge to M,
Yeah.
but that in a sense is already assuming that it converges, like we don't even
Right.
know that it converges.
Right. Maybe a better idea, but it's just saying that if it doesn't converge to L, then there won't be points.
Marco, do you want to finish this off? Finish the statement. Suppose you don't converge to L. In other words,
There exists some epsilon.
there exists a bad epsilon.
Such that there does not exist, or we can do a for all not.
Right. There exists an epsilon such that for every n, there is some n bigger than n such that the distance of a sub n to L is bigger than or equal to epsilon. Right? That's the negation, right? For every epsilon, there's an n that past which blah, or there's a bad epsilon so that no n works, right? No n works. Whatever n you choose, there's somebody past it that fails. Okay. Right? So that would say that, okay, so here's your L, and there's some bad epsilon. Let's call it epsilon 0. Okay. So there's this epsilon 0 that no matter what you do, there's somebody past you that's outside of the neighborhood. Okay. Somebody past you that's outside the neighborhood.
So L is not accumulation.
Well,
That-
accumulation point just means you have points at some an that are near it.
Yeah.
It doesn't actually do with the linearity of
Yeah,
an.
so remember what accumulation point means, that accumulation point for the set of values, right? Accumulation point for the set of values means that given any epsilon, you can find some value inside here.
But, okay, so if we're saying past.
Right, that value could occur at this point, say, right? Maybe it occurs here, maybe it occurs here. Okay, so having these guys outside doesn't violate the accumulation pointiness of this thing.
Because you could have stuff after that.
But then it's not Cauchy because it's not convergent.
So see if you can do it. So we're not gonna get a contradiction with the accumulation point status of L, but maybe we get a contradiction with Cauchiness.
So using that same contradiction as before, then you have a point A at AN that doesn't fall in that. So if you take AN minus AN minus 1, you have that distance, then that's larger than your epsilon.
So you're
Therefore,
saying
it can be Cauchy.
that the guy before, where is this guy?
It's right before whatever arbitrary n. So if
Is it, are you saying that it's inside the L neighborhood? How do you know that the right guy right before is in the L neighborhood?
some other point AN.
Some guy is, yeah, some guy is,
Okay.
certainly, right? So you know that, right, so, right, so
yeah.
by Cauchiness, right, since you guys are really close to it, maybe I shouldn't have said that because it's too much of a clue. But you guys are really close to it, right? By Cauchy, since this is Cauchy, right?
Then every distance, subsequent distance is supposed to get closer and closer to 0 or epsilon.
Pairs of points have to get closer and closer to each other, right? So
the difference in ANs has to.
right, we know that for epsilon, you know, roughly speaking, a sub n minus a sub m goes to 0. Right? That's not the rigorous idea, but right, for all epsilon greater than 0, the existent n is such that if you're past that guy, then the distance is smaller than epsilon. Okay.
So we have to turn the a sub n minus L statement into something that looks like a sub n minus m is greater than or equal to epsilon.
Right.
That's our contradiction.
Yeah. So yeah, you're going to use this thing and somehow get a sub n minus a sub m is greater than epsilon. Right. You've got a sub n minus L is greater than this epsilon naught. Right. You've got this bad thing here. Right.
So you also know that a sub m minus L is greater than or equal to epsilon 1.
This is greater than what?
A sub m.
A sub m is what? Less than. Wait, no.
A sub m minus L is greater than or equal to epsilon 1.
What's epsilon 1?
A different epsilon greater than 0.
Then you can't compare them.
Just some, so epsilon 1 is just some number.
Can you restrict m to being larger than little n? In which case you could do what Mitchell's trying to do, which is to say that the a sub m minus L has to be greater than or equal to epsilon naught.
Okay, so you say, okay, well, look, I know that I know that this guy is Cauchy, right? I know this guy is Cauchy, so, you know, there's some, I don't know, there's some n prime. There's some n prime such that everybody past this point is within epsilon of each other. Okay. So, so you're saying, choose m bigger than n, right? And maybe I should call this guy n naught. Right. Is that all right? Call this guy n naught. Choose m bigger than n naught. So you know then that then the distance between a m and a n naught is smaller than our epsilon.
So
Are you trying to say that this is any m or for all m's? Because if it's for all m's, then that means that there's a new accumulation or a new.
Well, it's for all m, right?
Mm-hmm.
Right? I mean, as long as you're m, right? So, well, I mean, that's assuming, actually, that's a mistake because, I'm sorry, you don't know that how do you know that your n naught is bigger than that m prime? Well, you do, actually, right? Because you use the, right? You use this fact that for every n, this sort of thing happens, right? So you use the n prime from here and here, and you get an n naught past it that is outside of epsilon naught,
Mm-hmm.
right? So you say, okay, look, I'm going to take my n prime. I know that there's some n naught past it that is outside of epsilon naught. Right? I know that there's somebody past that point outside of epsilon naught. But by Cauchiness, I know that past this guy, everybody's close to this epsilon naught, close to the a sub n naught.
Mm-hmm.
Right?
Therefore, that an also has to be close to L. Or the an naught also has to be close to L.
Right, or if you're going for the contradiction, right, you want to, I mean, yeah, you could go that way, but it's a little bit clearer to me to say that the guys, everybody outside here will be away from L, right? But then L is not an accumulation point.
Mhm. Okay.
So your homework, part of your homework will be to write this up. Okay, and have your groups here on Monday for the group presentations, please. Yeah, I was thinking, you know, the first couple group presentations I wouldn't grade, but just tell you, like, give you feedback. Because otherwise, if I'm grading from the beginning, it's sort of arbitrary. Like, how do you know what I want? But for the first two presentations, I thought, okay, I'm just going to tell you what you need to work on.
We're going to have more presentations before the final?
Yes. Yes. I think it's just one problem at a time. Okay, so yeah, I will actually send out another group project for you all to work on soon, maybe today, and also the groups, because I'll mix up the groups a little bit.
What are exams?
Sorry?
Exams.
I don't have them yet, sorry. It's been a busy week.
I'll think about it on Monday. I'm gonna take the weekend.
Thanks, Professor.
Okay, you're welcome.
Thank you.
You're welcome. See you. See you.
Professor?
Hey.
Because that's our group write-up, could you bring it to class on Monday?
Oh, yeah. I mean, if you want to take it, you can take it. But do you want? If you
Yeah,
don't,
sure.
I'll just keep it.
I mean, if you're going to bring it to class on Monday.
Yeah, I'll bring it to class. Yeah.
Thank you very much.
You're welcome.